Alright, welcome back. Our subject here is I'm doing a comparison test with these two Darlington devices here. They're both optocoupler isolated from the low voltage circuitry. This one is a TIP 120 on this heatsink, and this is the one you've seen in other videos, the MJ 10005. Of course, you can see the motor up here. If you look at the motor real close, there's a slight difference in speed when I reverse direction. The two power MOSFETs are identical, drop at nearly the same voltage. There is a difference between these two Darlington setups. The TIP 120, when it's running 3.6 amps or so, drops 2.75 volts from collector emitter. The MJE 10005, under the same conditions, drops 2.25 volts. This is the actual test setup that I also use to test for some other transistors. Over here's my two batteries giving me 26.5 volts at high current, two 10 ohm, I guess 40 watt resistors or whatever in parallel to give me 5 ohms for a load. There's my TIP 41A assembly, the optocoupler assembly, and there's the MJE 10005. I did not use these parts here. That's a different article. That's a different set of switches, and I still switched on the optocoupler on and off this with an Arduino. I'll be discussing some transistor switching circuits, mainly power transistor switches. So let me show you around my test setup. There's not a lot to see with it. This is a pair of batteries, and these parts and this charger were salvaged out of an electric wheelchair. This is its power system, charging system, and the whole works. Through this terminal strip, I can get 12 or 24 volts at a bunch of amps. And so that's where that power comes from. Thought you might like to see that. Let's look closer at the actual test circuits. All of this went back to some tri-state switches and H-bridge motor controls from earlier videos. We're not concerned about that. This is the optocoupler. In this case, it's turning on a TIP 120. The idea of this all along was to get rid of the headaches involved with Q1. It's a P-channel MOSFET. And the headache being is the voltage gate source was limited to 20 volts. So I could not run this circuit above 20 volts without damaging Q1. So what this did is it allowed me to get rid of the headaches associated with a P-channel MOSFET by using bipolar transistors. This is my own generic symbol of what amounts to is a NPN transistor solid state relay that I call SR1. When I connected it as shown, I connected the collector side, of course, to 26.5 volts. I switched it on through the LED circuit with an Arduino. And I had a voltage collector emitter drop of 2.4 volts. And then I had my 5 ohm load. If you look at it up here, your current, and it pretty well measured out to be that, you had to subtract 2.4 from 26.5 volts, divide by 5 ohms, and you have approximately 4.8 amps. So that's what it does. It's a high side switch. Why do I drop 2.4 volts? We will discuss that in the next part. Okay, here's an example of the two currents. Here's the MJE 10005. And in the case, what I tested it as, it was a 4N26 optocoupler, a TIP41A. And of course, this being rated for 400 volts, this is rated at 60. But your biggie, this is rated for 30. Since I was using a plus VCC of 26.5, a 4N25 works just fine. Everything's within range. I didn't do the checks on this, but this works very similar. You would be, if you wanted to go to 48 volts on plus VCC, you would have to change the optocoupler to a PC817 because you'll probably damage the 30 volt model. All right, the results of the test were interesting to say the least. Q2 is the MJE 10005. Q1 is a TIP41A. And of course, this was a H11A1 type optocoupler. Here's my actual measured values. The current A was only 120 microamps. Okay, A is also the base current of Q1, which is also 120 microamps. The emitter current, well, the collector emitter current of Q1, the TIP41A, measured out at 30 milliamps, while the current at IC was around 4.8 amps. And I'm doing conventional flow for any of you that want to whine. Well, just so you know, because somebody was complaining. I get one complaint that somebody wants conventional flow, the other person wants electron flow. Electron flow is correct, but I'm using conventional flow because this is what you've been mistaught in college and what you're used to. Again, conventional flow, positive to negative. All right, let's note some interesting facts here. VCC, VCE, voltage collector emitter on Q2, here to here, is 2.4 volts. But what's interesting is if I measure the voltage from emitter to base on Q2, that's 1.6 volts. And if I measure the emitter base voltage on Q1, that's 0.6 volts. 0.6 plus 1.6 is 2.2 volts from the emitter of Q2 to the base of Q1. The voltage drop across the optocoupler was so small I couldn't really measure it, so I disregarded it. So if you subtract 2.2 volts from 2.4 volts, I had a remaining difference between the collector and emitter of 0.2 volts to drive the current, to derive enough current from the collector side to turn on Q2 and Q1. In fact, this may be funny, I actually took out Q1, connected the optocoupler output directly to Q2, and it worked about the same. So I really didn't need this because this voltage collector emitter is going to hang around 2. In fact, it dropped when I removed this to about 1.8 or something like that. It's going to be 0.2 above the combined emitter base voltages of these transistors, and that difference supplies the small current that turns on these devices and let your resistor sit there and get good and hot. As a final note, this particular transistor configuration is known as a common collector configuration. That completes this video. I would appreciate it if you hit the like button, and you can follow the link to my, where is it? Website at www.bristolwatch.com to get these schematics and the other notes that went with this video. Thank you for listening in, and have a great week.